This video introduces axisymmetric elements for finite element analysis, and our focus will be on how they differ from the more standard plane stress or plane strain 2D elements. Although axisymmetric elements are 2D element types, they do fundamentally differ with plane stress and plane strain in a few key ways. One of them is that we're going to be using cylindrical coordinates to define the deformation of the element rather than doing things in the Cartesian coordinate system like for plane stress and plane strain. So this slide introduces that cylindrical coordinate system. In particular, as you can see here, we have displacement in the radial direction being called u instead of the x direction as for Cartesian. Displacement in the theta or tangential direction is called v, and finally displacement in the z direction or axial direction is called w. So u, v, and w are being used, but they are three different directions. The other thing that changes is then the relationship between strain and displacement. So we need to look at that for cylindrical coordinates in general, and then on the next slide I'll go through how that changes for a axisymmetric problem. So first off, epsilon r, what you would expect, du dr. Epsilon z, also what you would expect, dw dz. But for epsilon theta, we actually pick up a non-derivative component here. U over r is part of the strain in the theta direction. And this makes sense. If we increase the size of something that is defined by cylindrical coordinates, so we move in the radial direction, what we're really doing is expanding. So we're generating hoop strain. That's what that term represents. In addition, we have three shear strains that are associated with the cylindrical coordinates. So now let's take a quick look at what happens if we impose the axisymmetry condition. So axisymmetry means nothing changes with respect to angle. So what that means with these strain terms here is any derivative with respect to theta disappears. By definition, if nothing's changing with respect to theta, that goes away. In addition, we get rid of any translation or displacement in the theta direction. You can't have a theta translation if nothing changes with respect to theta, because otherwise all you've described is a simple rotation of the entire body. So we drop those terms as well. So that brings us to our axisymmetric 2D formulation. What we have is this idea for axisymmetry that nothing changes with angle. Specifically, as we talked about, we have no translation in the theta direction, and the two shear strains that involve theta both go to zero because of the terms I crossed out on the prior slide. So that leaves us with four non-zero strains. Epsilon r is du dr, epsilon z is dw dz, epsilon theta is now u over r because the derivative with respect to theta disappeared, and then we have the one shear strain between r and the z direction. Now, one quick thing I'll point out here, the order that I've listed these is the order that is sometimes used, and that's compatible with the x and the y direction for plane stress, plane strain. Here, r and z are the directions of the plane that we are looking at. It's basically the gray surface showed in this view. So we have r and z shown in the plane view. However, some other codes will use epsilon r, epsilon theta, and then epsilon z. So you want to be a little bit careful if you're trying to look in at the details which one comes first, z or theta, in the formulation that you're looking at. So we want to write this system of four equations in vector form. When we do that, this is what it looks like. And this gives us a definition of our partial derivative matrix operator, different from what we've been doing for plane stress and plane strain. And the main difference that we can see here is that we now have four rows in this partial derivative matrix operator and four strain terms. So now that we've talked about the strains, let's go and look at this simple three-node triangular element and what would the shape functions look like for that. As it turns out, if we have the degrees of freedom corresponding to the z and the r direction, so we have a total of 6 degrees of freedom, this is going to allow us to generate the shape functions, but it's going to be exactly the same process as we used for the xy coordinate system triangle. In other words, if we simply change x to r and y to z, then the shape functions will be the same ones we would develop if we did it independently. So the shape functions then for a right triangle element, not the general triangle, but just this right triangle like what I developed in the prior video, are the ones shown here. So when we put that into matrix form, we have our u vector, which now consists of translation in the radial direction and translation in the vertical or axial direction, so that's u and w, is equal to the shape function matrix, which has 6 columns and 2 rows, and that's multiplied by our degree of freedom vector. Continuing with this three-noted element, let's find what B looks like. And here we're going to experience some differences because remember that we just derived this partial derivative matrix operator that's shown here, and we're going to have that act on our shape function matrix. But now our B matrix, instead of having 3 rows, is going to have 4 rows because we have 4 rows in the partial derivative matrix operator. So the end result is this expression. And one thing that should stand out as being distinctly different, the third row here has no derivatives. Those are the raw shape functions, and then we're just dividing through by the radius. That introduces some interesting effects that we'll talk about in another slide. When I actually evaluate each one of my shape functions, take the derivatives, or simply plug in the quantities, in the case of the third row there, I get this expression. This looks like it's constant with the exception of that third row. And in fact, what we need to do, imagine if we had one of these triangle elements that's sitting right on our z-axis. That means r would be 0 on the left-hand side, which would mean 2 of those terms in the third row would blow up. They would become infinite. Obviously not a good thing in an FE formulation to have something that goes infinite just because it happens to sit on the axis of symmetry. So what we're going to do is say that this element really should be a constant strain element, so we're going to make it a constant strain element. So we're going to evaluate B just at the center of the element, at B over 2 and H over 2. And that condition gives us this final B matrix. That's the general formulation used for an axisymmetric B triangular element. The last thing I want to talk about is the axisymmetric formulation relating to stress and strain, how they're related to each other. What we're going to do is consider this like a 3D problem, and then we're going to see the relationship is actually the same as for a Cartesian coordinate system. In particular, if we look at stress in the radial direction, it's going to be directly related to the strain in the radial direction and then inversely related to the, or negatively related to the z and the theta direction. Similarly for sigma z and for sigma theta. So the sigma theta is the new one here because what we have is a hoop stress that we have to keep track of. Even though when you do an axisymmetric analysis, you're simply looking at a plane, a slice through in the radial axial direction. So the theta is perpendicular to that, but that strain is very important to controlling the deformation of a part. So we need to capture the sigma theta to have a good description of what's going on in an axisymmetric model. And then lastly, we have the shear relationship, which we rewrite in terms of Young's modulus, as we do with a plane stress analysis, a plane strain, or even a 3D Cartesian analysis. When we put all these together into matrix form, we want it to look something like a sigma vector equals a D matrix times a strain vector, and this is the matrix that we end up with. So this defines the D matrix for an axisymmetric problem. Notice that the big difference here is the size of the two vectors, the strain and the stress vector.